Chapter 9, Section 10, Taylor and Maclaurin Series, Part 1. It is time to acknowledge the elephant in the room. Until this lesson, we have only told you how to write a power series representation for a function by using either a geometric series or a known power series, such as the series for sine of x. We haven't told you how to find the known power series. That is the focus of this lesson. Let's consider an example. Let f of x be the function e to the 2x. We would like to find a degree 4 polynomial, q of x, such that q of 0 and f of 0 are the same. The first derivatives are both the same at 0. The second derivatives are both the same at 0. The third derivatives are both the same at 0. And the fourth derivatives are both the same at 0. First, let's find the derivatives of f and evaluate them each at 0. So first of all, since f is e to the 2x, f of 0 is 1. The first derivative is 2e to the 2x. Evaluating at 0, we get 2. The second derivative is 4e to the 2x. Evaluating at 0, we get 4. The third derivative of 0 is 8e to the 2x. Evaluating at 0, we get 8. And the fourth derivative is 16e to the 2x. Evaluating at 0, we get 16. Now let's do the same thing with q of x. Again, let's evaluate q at 0. Since all the terms except the first, a, contain a variable x, plugging in 0 gives us just a. The first derivative of q is b plus 2cx plus 3dx squared plus 4ex cubed. Substituting in a 0, all the terms except the b disappear. The second derivative is 2c plus 6dx plus 12ex squared. Again, substituting in 0, we're left with just the constant term, 2c. The third derivative is 6d plus 24ex. Again, substituting in 0, the constant term 6d is the only one that remains. And lastly, our fourth derivative is 24e. Since this is a constant term and there are no terms to the variable, the fourth derivative of 0 is 24e. This gives us a series of equations which we must now solve. For q of 0 equaling f of 0, we get that a is equal to 1. For the first derivative at 0 equaling the first derivative of 0 for f, we get that b is equal to 2. But starting with the second derivative, third and fourth derivatives, it gets a little more interesting. The second derivative of q at 0 was 2c, and the second derivative of f at 0 was 4. So in this case, c is 2. The third derivative at 0 was 6d and 8. So in this case, d is 8/6 or 4/3. And the fourth derivatives were 24e and 16, respectively, giving us e of 16 over 24 or 2/3. Now that we know a, b, c, d, and e, we can say that q of x is the polynomial 1 plus 2x plus 2x squared plus 4/3 x cubed plus 2/3 x to the fourth. But can we generalize this idea? Let's look a little more closely. We'll note that the first derivatives were the same at 0, so b was equal to 4 prime f prime of 0. A was equal to f of 0. C required a little more work, that c is the second derivative at 0 divided by 2 factorial. D is the third derivative at 0 divided by 6, which is 3 factorial. And the fourth derivative at 0 divided by 24, or 4 factorial, gave us the e value. So a more general equation for q of x is f of 0 plus f prime of 0 times x, plus the second derivative at 0 divided by 2 factorial times x squared, plus the third derivative at 0 divided by 3 factorial times x cubed, plus the fourth derivative at 0 divided by 4 factorial times x to the fourth. This is a Maclaurin polynomial of degree 4. If f has a power series representation expansion at x equals a of k equaling 0 to infinity of c sub k x minus a to the k with a radius of convergence of r, then its coefficients are given by the formula c sub k equal the kth derivative of f evaluated at a divided by k factorial. To put a little more explanation to this, we're saying that the power series f of x equaling the sum from k equaling 0 to infinity of the kth derivative of f evaluated at a divided by k factorial times x minus a to the k is a Taylor series of f about or centered at a. The special case where a equals 0 is called a Maclaurin series, in honor of 17th century Scottish mathematician Colin Maclaurin. For many problems, we only require the power series to obtain an approximation. We did this with integrals in the previous lesson. In these cases, we will use a Taylor or Maclaurin polynomial of degree n. In the first example of this lesson, we wrote a polynomial of degree 4 centered at 0, which was the Maclaurin polynomial of degree 4. In some cases, we need an approximation of our function at a value that's away from 0, which requires a Taylor polynomial. Let's find the Taylor polynomial of degree 5 for y equals ln of x. Since ln of 0 is undefined, we will center it at 1. First, let's take a look at our values. Well, if f of x is ln of x, f of 1, ln of 1, is 0. But the first derivative is 1 over x. Evaluating that at 1, we get 1. The second derivative is negative 1 over x squared. Evaluating that at 1, we get negative 1. The third derivative is 2 over x cubed. Evaluating at 1, we get 2. The fourth derivative is negative 6 over x to the fourth. Evaluating at 1, we get negative 6. And the fifth derivative is 24 over x to the fifth. Evaluating at 1, we get 24. Using this information, we can now start to write our polynomial. First, the general form. The fifth degree Taylor polynomial is f of a plus first derivative of f at a times x minus a plus the second derivative of f at a divided by 2 factorial times x minus a squared, and so on until we get to the fifth derivative at a divided by 5 factorial times x minus a to the fifth. Substituting our a value of 1 in, and then the corresponding values for each of the derivatives as well as the original function evaluated at 1. And then a little bit of simplifying. We obtain that the fifth degree Taylor polynomial that approximates ln of x at 1 is given by x minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed minus 1/4 x minus 1 to the fourth plus 1/5 x minus 1 to the fifth. The next issue is, how good is a Taylor approximation? In the next video, we'll consider what's called the error bound on a Taylor and Maclaurin polynomial.